A very good morning to all of you. Today I am going to discuss, rather I am going to continue my discussions on DSC, TCR, SVC. Okay, I will write here DSC, TCR, SVC continued. I already have delivered one lecture, that's last lecture on this topic, and today's lecture is a continuation of our discussions on this type of SC, third type of SVC, that is DSC, TCR, SVC. Now I am going to discuss with you the functional control scheme of this type of SVC. I will write here functional control scheme. Now this functional control scheme will look like this. This is IQ, that is reactive current reference. Okay, now here it is required, this block represents a required capacitor and a required capacitive and reactive current compensation. And then I have a block here which is thyristor switched capacitor 1. Let me draw it again. DSC 1 OnOff Control, OnOff Control. Now a request for DSC1 OnOff will come from this block. This is DSC1 OnOff request, which will come from this block. I'll explain in a minute's time. This is DSC2 OnOff request. OnOff request. So on, you may have n number of DSC brands connected in your SVC. So this is DSCN OnOff request. OnOff request. How many TSC brands have to be turned on at a time? That will be decided by what is the reference reactive current that is required. Okay, now this reference reactive current may be capacitive current or it may be inductive current. If reactive power is to be generated and injected into the transmission system, then it will be capacitive current, and this block will decide about how many TSC brands have to be turned on, and accordingly it will send a request to TSC turn on off blocks, control blocks. For example, if only one TSC branch has to be turned on, a request will go to this control block and it will turn on TSC1. If two TSC branches have to be turned on, then another request will go to a similar block, and that will generate the firing pulses for the for switching in or for turning on second TSC branch. Similarly, there may be n number of TSC branches. TSC is thyristor switch capacitors. How many of them will be turned on at a time will be decided by this IQ ref. That means how much reactive power compensation has to be done. Now this is the this is our TSC. Say one TSC. I will show one TSC branch. There may be n number of TSC branches. Let me show just one TSC branch. So this is it, and there may be many other type of TSC branches. I am not showing them, and I am showing a segmented TCR. TCR also I am showing. One TCR. This is L by 2, L by 2. That's it. The applied voltage or the bus voltage is V, and the total current is I. Now this capacitor voltage, with the help of a voltage sensor, is sensed and it is fed to this block. Similarly, the voltage across this switch, let us call this switch as T. The voltage across this switch T is sensed by another voltage sensor, and this signal also goes to this block. And in addition to this, now this TSC1 on-off control, whenever it gets request from this, it will issue the control pulses for the firing of TSC1. This is our TSC1. Okay, it will issue the control pulses. I am showing the control pulses like this, and the control pulses will go to the gates of the two thyristors, anti-parallel connected thyristors, and it will turn the switch on, of course at alpha equal to 90 degrees, because TSC, when TSC turns on, it turns on fully, and for that alpha is equal to 90 degrees, so this TSC branch is turned on. Similarly, if another TSC on-off request goes to this type of block, TSC2 on-off control, then control pulse will go to another TSC, which I am not showing here. Okay, so how many TSC branches will be turned on at a time depends upon how much reactive power compensation has to be done. And then, in addition to turning on TSC branches, n number of TSC branches, your controller will control the firing of this TCR. This is TCR. Okay, for that purpose we have another block here, control block, which is called DSC firing delay angle control. TCR, not TSC, TCR firing delay angle control. So it will issue, this block will issue firing pulses at a particular alpha. Okay, and it will generate the control pulses, and those firing pulses will be issued, and they will be given to the gates of these anti-parallel connected thyristors, SCRs. Okay, at a particular value of alpha. What will be the value of alpha? That depends upon how much reactive power has to be absorbed by this TCR. So this is basically the functional control scheme. Overall scheme, the schematic diagram or the block diagram of complete functional control scheme of this type of SVC, that is DSC, TCR, SVC. Now this control scheme fundamentally performs three functions. What are the three functions it performs? So it performs, I will write here, three functions. I'm going to discuss those three functions one by one. The first function is that this scheme, this complete control scheme, it calculates the number of DSC branches to be switched in for capacitive reactive current compensation. Okay, depending upon how much reactive power compensation has to be done, it will calculate how much it will determine the number of TSC branches which have to be turned on. For example, here I am showing only one TSC branch. There may be n number of TSC branches connected in parallel. How many TSC branches have to be turned on simultaneously? That depends upon how much capacitive reactive current is needed to be generated or is needed to be produced, which will be decided by how much reactive power compensation has to be done. What is the total reactive power demand of the load? What is the total reactive power which is flowing on the transmission line? So that will decide the number of TSC branches to be turned on. So the first function is, it determines the number of, I will write here, the number of TSC branches to be switched in. Switched in means to be turned on for capacitive reactive current compensation. Reactive current compensation, that means for reactive power compensation. It basically finds, once it knows how, once the controller knows how much reactive power compensation has to be done, it then calculates how much reactive capacitive current has to be generated by TSC branch which have to be switched in. Okay, and it also determines the magnitude, I will write here, magnitude of reactor current. Reactor, that is TCR current. Reactor current means TCR current to cancel the supply surplus capacitive current, to cancel the surplus capacitive current. Try to understand this point. This is very important. Once, let us suppose, depending upon the reactive power requirement, which is, I mean, this, where do we get, where from we get this IQ ref? There is some other block which I am not showing. I mean, your controller calculates, finds what is the reactive power requirement on the transmission line, and then it finds the reactive current IQ ref, which has to be generated by your SVC, and that reactive current IQ ref determines, it is indicative of how much reactive power compensation has to be done. Instead of writing in terms of reactive power, which is an abstract quantity, what we do is we find the reactive power compensation in terms of reactive current, because it is very easy to sense the currents, to calculate the currents, rather than to sense and calculate the reactive power. Once the reactive power requirement on the transmission line is known, depending upon how much industrial load is connected, what is the load power factor, how much inductive reactive power is required by the load, how much reactive power compensation is required, then your one of the mathematical blocks that calculates the reactive power requirement in terms of reactive current, IQ ref, that is reference reactive current. So this much is the reference reactive current, which determines, or which is indicative of how much reactive power has to be injected into that transmission system for reactive power compensation. Once this current is known to us, which determines the reactive power compensation, it goes into this block. What will this block do? It is a mathematical block. This block will determine the number of DSC brands, because for reactive power compensation, for injecting the reactive power into the transmission system, we need to turn on thyristor switched capacitors. Now there may be n number of thyristor switched capacitors. How many of them have to be switched in at a time? That depends upon this requirement. So depending upon this requirement, this block calculates, or it determines the number of TSC branches to be switched in for capacitive reactive current compensation. Let us suppose 4 TSC branches it switches in simultaneously. So therefore 4 TSCs will be turned on, and they will inject reactive power, and they will generate the capacitive reactive power and inject that reactive power into the transmission system. Now this reactive power requirement may be more than, I mean, this injected reactive power, capacitive reactive power, which is injected into the transmission line by all the 4 TSC branches, it may be more than the reactive power requirement. Okay, so therefore there is a surplus reactive power. In terms of currents, some of the current, the capacitive reactive current which is injected into the transmission line, it will be more than IQ reference. In terms of reactive power, the injected capacitive reactive power is more than the reactive power compensation required. So we deal in terms of current. So total capacitive current which is injected into the transmission system, that may be more than the reference reactive current. So the surplus reactive current, which is IQ ref minus injected current, that has to be absorbed or that has to be drawn by the thyristor controlled reactor. So the magnitude of inductive reactive current will also be calculated by this block, and depending upon how much reactive power this TCR has to absorb in terms of the reactive current, the inductive current, it adjusts the delay angle alpha of TCR and issues the firing pulses to the switches of this TCR. TCR turns on, and it compensates for, or it cancels the surplus capacitive current. The total capacitive current IC may be greater than IQ ref. This. So the surplus reactive current, which is IC minus IQ ref, has to be absorbed or has to be cancelled. And which component of SVC will cancel that? Thyristor controlled reactor. And how much current, depending upon how much current has to be cancelled, Ix, magnitude of Ix or magnitude of IL. The delay angle of this thyristor controlled reactor is controlled, I mean it is determined by this TCR firing delay angle control. Okay, depending on how much reactive current it has to cancel, excess or surplus reactive current, it has to cancel, and then it fires the TCR. TCR absorbs or it cancels the surplus capacitive current. In other words, it absorbs the surplus capacitive reactive power or leading wires which are there flowing on the transmission line, and hence it balances for reactive power compensation. So the perfect reactive power compensation will be done. So this is the first function which will be performed by this functional control scheme. I repeat, the first function is that it determines, depending upon the capacitive reactive current which has to be injected into the transmission line, which depends upon the reactive power compensation. It determines how many DSC branches have to be switched in, and then it issues the firing pulses to all those DSC branches at alpha equal to 90 degrees and switches in all those DSC branches. Now when all the DSC branches are switched in, okay, the injected capacitive reactive current may be more than the reference current, and therefore the surplus current, which is IC minus IC minus IQ ref, that surplus current is equal to the inductive current. That surplus capacitive reactive current has to be cancelled, and that will be cancelled by TCR. So this control scheme also issues the firing pulses to TCR at a given or at a particular delay angle, depending upon how much surplus reactive current has to be cancelled. So this is the first function. What is the second function performed by this block? Second function is that whenever it decides that, say, 2 or 3 number of TSC branches have to be turned on, we know that whenever the TSC branches have to be turned on, they have to be turned on in such a way that a transient free switching results. I have delivered a separate lecture on TSC, thyristor switched capacitor, and in that lecture I have discussed with you in details. I have tried to explain how transient free switching of a thyristor switched capacitor results in. So the second function of this control scheme is that it controls the switching of TSC branch, thyristor switched capacitor branch, in a transient free manner. I mean, you cannot switch in TSC arbitrarily anytime. The switching has to be done in such a way that transient free switching results in. Okay, and if you remember, there are 2 rules which have to be followed, rule 1 and rule 2, and following those 2 rules, transient free switching of TSC branch results, or transient free switching of thyristor switched capacitors results. So therefore the first function is to determine the number of TSC branch to be turned on, and to determine the delay angle of TCR in order to cancel the surplus capacitive reactive current. Second function is that once the controller decides how many TSC branches have to be switched in, then those TSC branches have to be switched in a transient free manner. So therefore it controls the switching of all the TSC branches in a transient free manner. That is the second function. Okay. What is the third function? Third function is it determines the firing angle control or firing delay angle of this TCR. This is the third function. Controls the firing delay angle of TCR. Okay. So these are the 3 main functions which have to be performed by this control scheme. First function, depending upon the capacitive reactive power requirement, which depends upon how much reactive power has to be injected into the transmission line, which depends upon the reactive power compensation required. Depending upon this IQ ref, this controller decides how many TSC branches have to be switched in. Okay, that is the first, and it also finds the magnitude of this TCR current, inductive current, in order to cancel the surplus capacitive reactive current. That is first function. Second function is that once the number of TSC branch to be switched in is finalized, then firing pulses have to be issued to all those TSC branch to turn them on, but they have to be turned on in a transient free manner. So that transient phase switching of all the TSCs is also performed by this control scheme. And third is that once the controller knows how much inductive current or reactive current has to be drawn by this TCR, or in other words, how much capacitive reactive power it has to absorb, it has to find the delay angle or firing angle of TCR. So it controls the firing delay angle of TCR. So these are the three main functions which have to be performed by this control scheme, functional control scheme. Okay. Now let us see how these functions are performed. First function is to determine number of DSC brands to be switched in or to be turned on. How does it find those number of TSC brands? How does your control scheme or control algorithm or controller find the number of TSC brands to be switched in? So what it does, the controller already knows what is IQ ref, what is the reference reactive current, IQ ref. And if you have one TSC, say for example, this is your one TSC, thyristor switched capacitor like this, and when it is connected across the bus voltage, transmission line voltage or bus voltage, corresponding to this bus voltage, when it is turned on, it draws some capacitive current IC. Since if there are 5 TSCs in parallel, all TSCs will draw same amount of capacitive current. They are of equal rating. Okay, it's not that this TSC will be of 10 MVA rating, another will be of 5 MVA rating. No, generally they are of same MVA rating. So therefore, before switching in the TSC branch, a preliminary action has to be done, and in advance your controller must know how much is the capacitive current drawn by one TSC alone. So then what it does, it divides this IQ ref by this capacitive current, IC. IC is the current drawn by one TSC branch. This is the TSC branch. Okay. IQ ref is the total current, which is to be total capacitive current, which is to be generated or which is to be produced by when all the TSC branches are turned on. So total required or reference capacitive current divided by capacitive current drawn by one TSC. It will give the number, it will give an integer, say n. And this n has to be rounded up to or rounded off to nearest or rounded off to next higher integer. That means, let us suppose this n comes out to be 6.6. That means 6.6 TSC branches have to be turned on, but that is meaningless. You may have either 6 TSC branches or 7 TSC branches. It's always an integer. Whenever your controller divides IQ ref by IC, where IQ ref is the total capacitive reference reactive current, total reference capacitive current divided by capacitive current drawn by one TSC branch, it will give you the number of TSC branches which have to be turned on. And if it comes out to be a fraction like this, 6.6, this number n, which comes out to be, for example, 6.6, it has to be rounded off to next higher integer. And what is next higher integer? 7. So instead of having n equal to 6.6, it will give n equal to 7. So therefore, your controller will know that 7 TSC branches have to be turned on. Okay. So this is how it finds how many TSC branches have to be turned on. And simultaneously, it has also to find what is the current drawn by your TCR. How much current TCR has to draw? IL. It has to find how much current will be drawn by TCR. This is TCR. How much current will be drawn by TCR depends upon what is the surplus reactive current. If IQ is the reference capacitive current, and when you turn on all the TSC branches, let's suppose IC is the total capacitive reactive current. Now this IC may be greater than IQ ref. So therefore, you have to find the difference between the two, IC minus IQ ref. it will be surplus capacitive reactive current, and this surplus capacitive reactive current has to be cancelled out, and this capacitive current, we know it is cancelled by an inductor, so therefore TCR has to be turned on, and this will give TCR current. How much current TCR has to draw? Okay, so therefore ITCR or IL alpha, inductive reactive current, which is a function of alpha, which is same as TCR current, ITCR, which is also a function of alpha. It is given by this equation, summation ICN minus IQ ref. N is the number of TCR branches which have been turned on. Let's suppose 5 TCR branches have been turned on. IC1 plus IC2 plus IC3 plus IC4 plus IC5 is the total capacitive current which is injected by these DSC branches, minus what is the reference capacitive current, which is this. If this is greater than this, it will find the difference between the two, and that difference between the two will be nothing but surplus capacitive current, and that surplus capacitive current has to be absorbed, that has to be cancelled, and that will be cancelled by firing of TCR. And how much is that current the TCR should draw? That is equal to this surplus capacitive current, and the surplus capacitive current is this, that is summation of ICN minus IQ ref. So this is how your controller performs these mathematical computations to perform the first function. The first function of the controller is to determine the number of TSC branches to be switched in. I have told you how to do that. IQ ref, your controller already knows, divided by IC, where IC is the current drawn by one TSC branch, and it is switched in. So that will give an integer. This integer, if it comes out to be a fraction, it has to be rounded off to next higher integer, and this will give you a number of TSC branches which have to be turned on. And when the TSC branches are switched in, okay, the total current, capacitive current generated by these or drawn by these TSC branches ICN, say for example IC1 plus IC2 plus so on. And what is the reference capacitive current? IQ ref. If there is a difference between the two, if the capacitive current drawn by the TSC branch is greater than reference capacitive current, then this difference gives us surplus capacitive current, which has to be cancelled, and it will be cancelled only if TCR is turned on. And therefore, in order to turn on the TCR, we must know what is the delay angle at which TCR has to be turned on. And delay angle we will know only if we know the magnitude of TCR current that is drawn by the TCR when it is turned on. And that IL alpha will be given by difference of this summation of ICN minus IQ ref, which is the surplus current which is to be cancelled by the TCR. So this is how first function is performed. Now second function is again a very important function. In the first step of the algorithm, your controller knows that n number of TSC branches have to be turned on. In the second step, it will now issue the firing pulses to n number of TSC branches and will turn them on. But you already know, I have already discussed with you that whenever a TSC branch is to be turned on, the TSC branch has to be switched in a transient free manner. Okay, you cannot just issue the firing pulse to a TSC branch arbitrarily, because if your controller arbitrarily at any instant issues the firing pulses to the TSC branch, all the TSC branch devices may get damaged because of high transient current, because of large magnitudes of current, transient currents. So for transient free switching, function number 2 will be performed in the step number 2 by your controller. What is that? What is second function? Second function is transient free switching of TSCs, that is to switch capacitors or TSC branches. For that purpose, you know that your controller has to follow two rules. Rule 1. Rule 1 is that if capacitor voltage is less than peak of the source voltage or bus voltage. What is V? V is peak of bus voltage or transmission level voltage, which is across the secondary of the transformer. So it is like this. This is, for example, your voltage, bus voltage, and its peak is this is its peak V. Okay, and if your capacitor voltage is this VC, and if this VC is less than V, then at what point your firing pulse should be issued to the DSC branch for transient free switching? If your controller issues firing pulses here, 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 then that will definitely result in very large transient currents, and it will instantly damage the switches of TSC, and TSC branch will get damaged. Okay, why? Because if firing pulse is issued, say somewhere here, the instantaneous value of applied voltage is more than capacitive voltage. So since the voltage, the instant at which the TSC branch is to be turned on, the voltage is greater than capacitive voltage, of course much greater than the capacitive voltage, it will result in large transient current like this, and that current will instantly damage the thyristor switches, the thyristor valves. So therefore the first rule, if you remember, is that the DSC should be switched on, should be turned on at an instant when instantaneous value of bus voltage is exactly equal to capacitor voltage. That means when voltage across thyristor switch is equal to 0. So this is the instant. This is the instant at which this is the instantaneous applied voltage or bus voltage, and this is exactly equal to VC. When instantaneous applied voltage or bus voltage exactly becomes equal to VC, capacitor voltage, firing pulse should be issued to the TSC branch, and TSC branch will turn on in a transient free manner. It will draw current like this. I mean, there will not be any transient current. Okay, this is your, for example, DSC branch, thyristor switched capacitor. This is capacitor voltage, this is switch voltage, this is your switch T. Okay, and this is the applied voltage V. What is voltage across switch? VT. It is applied voltage minus VC, voltage across capacitor. It is, let us forget about this inductor, small inductor. The total applied voltage is V, out of which voltage across capacitor is VC, and voltage across thyristor valve is VT. And what is this VT? It is equal to applied voltage minus VC. And at this instant, when instantaneous value of applied voltage is exactly equal to VC, so for V equal to VC, what is V minus VC? Since V is exactly equal to VC at this instant, this is equal to 0. That means voltage across thyristor valve will be exactly equal to 0. So therefore, a voltage sensor has to be placed across the thyristor valve, and whenever this voltage sensor gives a signal to your controller that VT has become equal to 0, that is voltage across thyristor valve has become 0, that is an indication that instantaneous value of applied voltage V has exactly become equal to VC. And rule 1 says that when V is equal to VC, that means VT is equal to 0, issue firing pulses to thyristor valves and turn the TSC branch on, and this will result in transient free switching of the TSC branch. I hope that is clear. So that is rule 1. This rule 1 has to be followed. Second rule is rule 2. The capacitor voltage may be greater than or equal to peak of the applied voltage. When capacitor voltage is greater than or equal to peak voltage, TSC should be switched in when VT, voltage across the switch, is equal to VT min. I will try to explain it with the help of this waveform. This is again instantaneous value of applied voltage or bus voltage, and this is peak of the bus voltage V. And this may be the capacitor voltage. Capacitor voltage may be equal to peak of the bus voltage or slightly greater than peak of the bus voltage. When this is the case, then your controller should issue firing pulse at an instant when VT is equal to VT min. When is VT equal to VT min? At the peak of the applied voltage. Here you can see firing pulse has to be issued to the TSC branch, because here voltage across thyristor valve is equal to minimum. It is VT min. And in fact, if VC is equal to V, if capacitor voltage is equal to peak of the bus voltage, then VT will be equal to 0, exactly equal to 0. That means the firing pulses should be issued, firing pulses should be issued at peak of bus voltage or applied voltage, at peak of the applied voltage. That is somewhere here. This is the peak. Now this voltage has positive peak, it has negative peak also. Sometimes your controller may issue, if your voltage sensor, it senses the peak of the voltage, it can sense positive peak as well as negative peak. And it may so happen that instead of issuing firing pulse at positive peak, for this case, it issues firing pulse at negative peak. What is the capacitor voltage? It is VC, and it is almost equal to positive peak voltage. So therefore firing pulse should be issued when applied voltage reaches the peak of the, positive peak. But if the applied voltage, if the firing pulse is issued instead of issuing at the positive peak, if your controller issues the firing pulse at negative peak, then a huge transient current will flow, because your capacitor voltage is VC, but you are applying, it is plus VC, but you are applying firing pulse at negative peak of the applied voltage. The large difference in the two voltages will be there, and extremely huge transient current will flow, which will instantly damage the thyristor values of the TSC branch. So therefore your controller should issue, your controller or your voltage sensor should sense the capacitor voltage. Not only it should sense the applied voltage, peak of the applied voltage, and not only peak, but it should also find the polarity of the applied voltage, whether applied voltage is at positive peak or negative peak. For example, if the capacitor is having plus VC voltage, then firing has to be done at the positive peak of the applied voltage. On the other hand, if the capacitor voltage is at minus VC, then the firing pulses have to be issued, or the TSC branch has to be switched in at the negative peak of the applied voltage. So the polarity of applied voltage is also important. So these are the two rules. So these two rules will be followed by your controller, and that will complete function number 2, that is transient free switching of TSCs. And how is this function 2 performed? Let me show the functional block diagram for this. Functional block diagram for transient free switching, of DSC branches, thyristor switched capacitor branches or thyristor switched capacitors. So it is something like this. Diagram is like this. This is C1. This is your switch, say S1, or let us call this T1. This is L1. You have TCR also. I am not showing. This is TSC1. Similarly, you will have TSC2, TSC3, and number of TSC branches, and then you will have TCR also. I am not showing that TCR. And this is the applied voltage V, or bus voltage. Okay. Then we have a block here. This block will measure value voltage. It will calculate value voltage and capacitor voltage polarity measurement. Value voltage and capacitor voltage polarity measurement. And that is done like this. A voltage sensor is placed across the capacitor, and voltage is sensed, and the sensor gives information about the capacitor voltage to this block. Simultaneously, it also gives information. There is another voltage sensor here across the thyristor switch, and this voltage sensor senses the thyristor voltage Vt. Okay, this senses the capacitor voltage Vc, and this sensor senses the voltage across thyristor value Vt. And these two informations are given to this block. Okay, then this is our, say for example, this is capacitor voltage Vc, and this is switch voltage VSW. Let us call this, instead of calling it Vt, we call it VSW, switch voltage. SW means switch, voltage across the switch. Then I have an AND gate here. I have one AND gate here. This is AND gate. I have two outputs from this VPOL and another is VSW. This is on request signal which comes from the block which I have already shown, on request. And another signal comes here which is VSW, switch voltage. Okay, I have another AND gate here. This is another AND gate, and to this AND gate, first signal is again same, that is on request. Second signal is this VPOL, voltage polarity, and third signal which comes externally is PT signal. And the output of two AND gates goes to an OR gate. This is our OR gate. This is AND gate 1 output, AND gate 2 output, and output of this OR gate goes to firing pulse generator. This is firing pulse generator, and it generates the firing pulses for the switches of TSC, and it issues the firing pulses to the switches of TSC and turns the TSC on. Let us see how transient free switching results in. Now let us see how rule 1 is followed by this block diagram. Rule 1 says that rule 1 is this. I will again draw the diagram for rule 1. This is peak of the applied voltage. This is the instantaneous value of applied voltage. This is peak, and this is capacitor voltage. Rule 1 says that if capacitor voltage is less than peak of the bus voltage or peak of the applied voltage, then the TSC branch should be switched in. It should be fired at the instant when V, instantaneous value of applied voltage, is exactly equal to capacitor voltage. That means when VT is equal to 0. This is VT equal to 0. Okay, so therefore rule 1 is followed by this functional block diagram like this. Rule 1, TSC is turned on if on request is equal to 1, that means this request is equal to 1, and VSW is equal to 1, that is output of this block is equal to 1. When will be VSW equal to 1? VSW will be equal to 1 if instantaneous value of applied voltage is exactly equal to capacitor voltage. That means VT is equal to 0. See, if this is the situation, if capacitor bank previously was on, then it was turned off for some time. While turning it off, we know that we turn off the capacitor bank. If you remember, we go back to TSC theory, the theory of the operation of TSC branch. I told you that a TSC branch or TSC is turned off only when current through the branch is 0, and when current through the branch is 0, the voltage across TSC branch is either at positive peak or at negative peak. However, let us suppose when TSC branch was turned off, says it was turned off here when I was equal to 0, I, and the voltage across capacitor was at positive peak, so VC was equal to V. But with the passage of time, if the TSC branch is not turned on for several hours, due to self-discharge, the voltage across capacitor may have reduced, and it may have gone below VC. That is rule 1, VC less than V. Voltage across capacitor has gone below the peak voltage to which it was previously charged, which is self-discharge. Then rule 1 says if this is the situation, that VC is less than V, then firing of TSC branch should be done, or TSC branch should be switched in when VT is equal to 0. When will be VT equal to 0? When instantaneous value of applied voltage is exactly equal to VC. Okay, so see what this block does. It continuously reads, senses the capacitor voltage, and it also senses the switch voltage, VSW or VT. This is VT, switch voltage. And as soon as this switch voltage, if case 1 is the, if this is the case, that is capacitor voltage has become less than the peak of the input voltage. As soon as instantaneous value of input voltage has become equal to capacitor voltage. Here, what is VT, voltage across thyristor valve? Voltage across thyristor valve is V minus VC. Since V is equal to VC here, so it is equal to 0. So a voltage sensor is connected across the switch. It continuously senses the voltage across the switch, and it finds that as soon as VT has become equal to 0, voltage across switch has become equal to 0, it gives an information to this block, and this block makes VSW equal to 1. VSW is the output of this block. It does not do anything with Vpol. Vpol is equal to 0. Okay, it makes VSW equal to 1, and this 1 then goes, so therefore second input to the AND gate becomes 1. So VSW equal to 1 means that instantaneous value of this source voltage or instantaneous value of bus voltage has exactly become equal to capacitor voltage, that is voltage across the thyristor switch has become equal to 0. So VSW equal to 1 means that VT has become equal to 0. As soon as this voltage sensor gives an information to this block that VT has become equal to 0, that is voltage across the switch has become 0, the block gives an output VSW equal to 1. VSW equal to 1 means that VT has become equal to 0. So the second input to this AND gate becomes high, and request is already there high, because from that block which I have discussed in the first functional block, that block will give on or off request to various TSC branches. Let us suppose it has to turn on this TSC branch, so on request will be high. It's already high. So both the inputs are now becoming high. On request was already high, and as soon as VT has become equal to 0, as read by the voltage sensor, this block makes VSW equal to 1. So both the inputs are 1. On request is 1, VSW is 1. When AND gate has both inputs high, the output will also be high. Okay, this AND gate output may be low, but this output is high. And OR gate works, OR gate output is high when either of the two inputs is high or both inputs are high. Since this input has become high, okay, so output of OR gate is 1. So 1 gives an information to the firing pulse generator that issue the firing pulses to this TSC branch. So it issues firing pulses to this TSC branch, and this TSC branch immediately turns on. Okay, so therefore if this is the case, that is VC is less than V, and as soon as VT becomes equal to 0, that means V has become equal to VC, VT has become equal to 0, and information goes to this block through this voltage sensor that VT has become equal to 0. It makes the output VSW equal to 1. On request is already 1. 1, 1, 2, both inputs are high, output is high, and when OR gate has one of the inputs high, output is high, and this high output gives an information to the firing pulse generator that you issue the firing pulses to the devices or thyristors of TSC branch, and TSC branch immediately turns on in a transient free manner, because at what instant does it turn on? It turns on at this instant. When instantaneous value of bus voltage has become equal to VC, that means when VT has become equal to 0, so it results in transient free turning on. Okay, so that is if this was the situation when rule 1 was followed. If situation is like this, that is, this is your instantaneous value of applied voltage, this is peak value of applied voltage, but VC is greater than, slightly greater than V, or it is equal to V. So VC is greater than or equal to peak of the bus voltage. At that time, rule 2 has to be followed by this functional block diagram. Rule 2 says that when VC is greater than or equal to V, then the device should be fired, the DSC branch should be turned on at the peak of the voltage. Okay, let us see how that is done here. So I will write here now, if this is the case, if VC is greater than V, then TSC branch is turned on if on request is 1, number 1. Okay, Vpol is also 1, because this AND gate has 3 inputs, on, Vpol and PT, and PT is equal to 1. Okay. Now on request is already 1. That means this there is a request from the other block that please turn on this switch in this DSC branch for reactive power compensation. So the first signal on is 1. So this input is 1. Then second input VPOL, third input PT should also be equal to 1. PT equal to 1 means that applied voltage has reached its peak. So PT is equal to 1 when instantaneous value of this bus voltage is equal to peak voltage. So as soon as input voltage, instantaneous value of input voltage reaches its peak, okay, so this PT becomes equal to 1. This is another signal which comes from some other block, and that block continuously reads the instantaneous value of bus voltage, and as soon as bus voltage reaches its peak, it makes PT equal to 1. So PT is equal to 1 when bus voltage becomes equal to peak voltage. So second. Now the problem is that, okay, your controller has got the information that it has to turn on this DSC branch, and it has also got the information that instantaneous value of bus voltage or input voltage has reached the peak, but it does not know whether it has reached the positive peak or negative peak, because it may so happen that if the capacitor voltage is plus VC and negative peak has reached, at the negative peak also this PT will be equal to 1. PT will be equal to 1 when V is equal to plus V or minus V. It may reach positive peak or negative peak. If the capacitor voltage is positive and negative peak has reached, then PT will become 1 for negative peak also. And if by mistake your controller issues firing pulse, generator issues firing pulses to thyristor switches, a large transient current will flow, because capacitor voltage is at positive peak and you are firing the TSC at negative peak of the applied voltage. The difference between the two voltages is too high, and that will cause destructive current, transient current, which will instantly damage both the valves of, and therefore TSC branch will get damaged. So therefore, in addition to getting an information that peak of the voltage has reached, your controller AND gate should get another information that whether it is positive peak or negative peak. Okay, that it will get from this signal. VPOL will be equal to 1 when, I will write here, I will write it here, VPOL is equal to 1. So the third input VPOL, which comes from this block, it is equal to 1. It is high when sine of instantaneous bus voltage or input voltage is same as sine of capacitor voltage. See what it does. This block has, there is a voltage sensor across the capacitor. That voltage sensor reads the capacitor voltage and gives an information to this block that capacitor voltage is positive or negative, because capacitor voltage may be plus VC or it may be minus VC, depending upon आपने previously कब ऑफ किया है TSC branch को. Your capacitor voltage may be either plus VC or it may be plus VC. It may be either plus VC or minus VC. So this capacitor voltage sensor gives an information to this block that capacitor voltage polarity is positive or negative. Let us suppose capacitor voltage polarity is positive. So it gives an information to this block that capacitor voltage polarity is positive. Okay. And it also gives an information. So therefore, when will be VPOL equal to 1? I already told you that VPOL will be equal to 1 when sine of V is equal to sine of VC. When the polarity of instantaneous value of applied voltage is same as polarity of capacitor voltage. That means if the capacitor voltage was positive and instantaneous input voltage is also going through positive half cycle, then it will make VPOL equal to 1. Okay, so VPOL is equal to 1. ये signal भी 1 हो गई. On request तो already high है. On request is already coming from other blocks, so this signal is 1. This input is also 1, and PT will be equal to 1 if PT will be equal to 1 when the applied voltage has reached its peak. तो जो ही applied voltage peak पे पहुंचेगी ना, ऐसा हो सकता है कि applied voltage is reaching negative peak. When applied voltage is reaching negative peak, then also it will give PT equal to 1. But at that time, VPOL will be equal to 0. because capacitor voltage तो plus VC है, but instantaneous bus voltage negative peak पे है. At that time V pole will be equal to 0. तो आपके दो inputs high होंगे, तीसरा input low होगा. AND gate will give high input only when all the three, high output only when all the three inputs are high. And V pole will be high only when instantaneous value of bus voltage V, it has the same polarity, same sign as the capacitor voltage polarity. And when that is the case, this block will give pole V pole equal to 1. तो ये V pole 1 देगा और जो V pole 1 है, all the three signals are high. On request is high, V pole is 1. V pole 1 means that capacitor voltage and instantaneous applied bus voltage both have same polarity, and PT equal to 1. PT will become 1 when the applied voltage or bus voltage has reached the peak, because the firing has to be done at the peak of the input voltage, and then output will become high. And OR gate में जब ये output high हो जाता है, input high हो जाता है, output will be high, and it will issue firing pulses to both the switches of the TSC branch, and TSC branch will turn on. So this is how the second function is performed by this functional block diagram, which is part of the earlier diagram which जो मैंने इससे पहले draw की थी. Okay, so the second function is performed by this functional block diagram. It ensures that transient free switching takes place for both the cases, when capacitor voltage is less than peak input voltage, or when capacitor voltage is greater than or equal to peak input voltage. दोनों के लिए the two AND gates are used. This AND gate is used for when VC is less than V, and this AND gate is used when VC is greater than or equal to V, and then accordingly transient free switching results. और तीसरे केस में थर्ड फंक्शन क्या है? What is the third function? Third function is that your controller has to determine alpha, firing delay angle control of TCR. And ITCR is a function of alpha, which is also equal to IL alpha, that is equal to sigma ICN minus IQ ref. ये current तो step number 1 में ही already your controller has found how much is the inductive current required to cancel the surplus capacitive current. This already knows, and once it knows, it gives this information to a mathematical block, and that block calculates alpha. Depending upon कितनी TCR current होनी चाहिए, it calculates alpha, and it issues firing pulses to the switches of TCR at the desired value of alpha, so that the surplus capacitive reactive current is cancelled by this inductive current drawn by the TCR. So this is how this functional block diagram performs the three functions, and it results in perfect capacitive voltage compensation. After this, I will discuss briefly with you VI characteristics, voltage versus current characteristics of DSC, TCR, SVC. The characteristics are very simple. This is IL, this is IC, this is origin 0, this is voltage V. It may be like this. This may be maximum inductive current. So this is inductive region. If your SVC is operating in inductive region, and here it may operate in capacitive region. If it is operating in inductive region, this is the maximum inductive current, and this is the maximum voltage across inductor, across TCR inductor, VL max. If it is operating in the capacitive region, then depending upon कितने TSC आपने on किए हैं, for example, this may be VC max, maximum capacitive voltage, and corresponding to that, this may be IC max, maximum capacitive current. This is BC, and this is 2BC. When one TSC branch is on, the susceptance is BC. When second TSC branch is also turned on, the total susceptance becomes BC plus BC, 2BC. And for that purpose, you need to know what is the maximum voltage across the TSC branch, VC max, and maximum capacitive current, IC max. So this is about the VI characteristics in inductive region of operation as well as capacitive region of operation. And finally, I will discuss with you SVC power losses. What are the various power losses which are taking place in this type of SVC? Let me first of all draw the characteristic, the losses. This is inductive region of operation, and this is capacitive region of operation, capacitive, zero losses. This axis is reactive power. Reactive power may be inductive reactive power if SVC is operating in this range, or it may be capacitive reactive power if it is operating in this range, and this y-axis is power losses. As usual, you have a filter there, harmonic filter, and filter has constant losses. So these are constant filter losses. Constant filter loss. Whether this TSC branches are on or not, TCR is on, and when TCR is on, filter is also on for eliminating or cancelling the harmonic currents. So therefore filter will have constant losses, power losses like this. And then this is TCR loss. TCR losses I will explain in a minute's time, and these are 1, 2, this is for example capacitor C3, this is capacitor C2, this is capacitor C1. Now here in the inductive region, IQ is equal to IL alpha. In the capacitive region, IQ is equal to IL1 alpha minus summation ICN. Okay. When SVC is not doing any compensation, when no reactive power compensation, or when it does a small amount of reactive power compensation. Let us suppose TCR is off. TCR is off. Only capacitive reactive power needs to be generated. Then what are the losses? Losses will be there in the capacitor, in the TSC branch. These are TSC losses. This is TCR loss. These are TSC losses. If no TCR, if no reactive power has to be absorbed, all the reactive power which is generated by the TSC branch needs to be injected. Then all the TSC branches, depending upon kitne TSC on it, there will be TSC losses. In addition to these filter losses, there will be TSC losses. So for example, if only switch 1 is on, this is the TSC loss. If second switch is also on, second TSC branch is also on, losses will increase. If third TSC branch is also on, the losses will be higher. But in addition, if this surplus capacitive current has to be absorbed, or it has to be cancelled by the TCR. That means if TCR has to absorb the surplus reactive power, then TCR will be on. And as the delay angle of TCR is decreased, as the TCR current increases, for cancelling more and more capacitive current, for absorbing more and more surplus reactive power, the TCR losses will increase. So these are various losses of TCR, of this SVC. Okay, at zero reactive power compensation, there are minimum losses. But as the reactive power, as the TSC branches are switched in, losses will increase both in TSC branches as well as in TCR branch. So there will be more and more losses. Okay. So therefore that's all about this response. As far as response time of this type of SVC is concerned, its response time is slower, or I should write response is slower than FC, TCR, SVC. Okay, because in FC, TCR, SVC, capacitors are permanently fixed. Here capacitors are switched in through TSC branch. And if you remember, I have told you while discussing TSC that when a TSC branch is turned off, in order to turn it on again, we have to wait for 1 cycle. So there is a delay of 1 cycle. So that's why TSC, TCR, SVC is slightly slower in response as compared to FC, TCR, SVC. Okay. So that's all about this type of SVC. So therefore this is the most preferred type of SVC. Its cost is minimum of all the SVCs, minimum in the sense because when no reactive power compensation is, because the TCR rating is lowest in this case. The rating of TCR is 1 by n times the total SVC rating. Whereas in FCTCR SVC, the rating of TCR is greater than the rating of the fixed capacitor banks. Okay. And since these DSC branches are used, okay, the DSC branches can be turned on or they can be turned off at will depending upon how much reactive power compensation is required. So DSC branches are turned on in steps, in discrete steps, and reactive power control is done then by delay angle control or firing angle control of TCR. So this is the most preferred type of SVC among the 3 type of SVCs which we have discussed over last 3 to 4 lectures. First type of SVC that we discussed was MSC TCR SVC, where the capacitors were switched through the mechanical switches. It's the slowest type of SVC. And then there are problems with the trapped energy in the capacitor banks, and in order to trap that, release that energy, some special provisions have to be made. And MSC TCR SVC, because of its sluggish response, is feasible only for those applications where frequent disturbances do not take place, where fast response is not required. On the other hand, the second type of SVC, that's FCTCR SVC, is the fastest SVCs because the capacitor bank is permanently fixed, but the rating of TCR is highest. The rating of TCR is greater than the total rating of SVC or total capacitive bank rating, MVA rating. So it is costlier, slightly costlier, but the response time is very it's the smallest response time. Response is very fast. The problem with FCTCR type SVC is that if during wide voltage disturbances or wide disturbances in the system, since the capacitor bank is always connected, it's there, and this during the disturbances, the capacitor bank may result in resonances with the system. Okay, and that resonance may create a lot of problem. Whereas in the third type of SVC, which is DSC TCR SVC, whenever wide disturbances take place, our controller will switch off all the TSC branches. It will take TSC branches out of the circuit. So therefore, there are no chances of resonances during wide disturbances. So therefore, among the 3 types of SVCs, TSC TCR SVC, which is the last type of SVC, third type of SVC, which we have been discussing over the last 2 lectures, it is the most preferred type of SVC. So that is all about thyristor-based shunt compensator. Actually, the SVCs, the 3 type of SVCs that we have discussed, that is MSC TCR SVC. Second one was FC TCR SVC, and the third type was TSC TCR SVC. They are all thyristor-based shunt compensators. Thyristor-based shunt compensators. They are shunt compensators because they are connected in parallel with the transmission bus, with the transmission system. They are all shunt compensators, but they are thyristor-based because the TCR is thyristor-based component. TSC is also thyristor-based component. So these 3 type of SVCs. So whatever the type of SVC, whether it is MSC TCR SVC, FC TCR SVC or TSC TCR SVC, they are shunt compensators but thyristor-based. In our next lecture, inshallah, we will discuss about shunt compensators, converter-based shunt compensators. Converter-based shunt compensator. There is another type of shunt, another category of shunt compensator that is not thyristor-based, that is converter-based, and that is called static synchronous compensator, STATCOM. So hopefully in the next lecture, we'll start discussions about the second type of shunt compensator, which is converter-based shunt compensator, that is static synchronous compensator or STATCOM. So with this, I will end my today's lecture. Wish you all the best. Thank you.